So, good evening, ladies and gentlemen. Welcome to the Halifax District Amateur Radio Society. A couple of faces I don't know. I'm Max down in G4 SDX, General Dog's Body. And what we're going to talk about tonight is what I call a super-Rybakov. If you attended the talk we gave, I think it was last year, on the Rybakov antenna, which is traditionally a fairly short antenna, multiband antenna, which is about 29 feet long, 5 and a bit meters, with a 4:1 Unun at the bottom of it, and then it's run back to a tuner at the radio end, and it gives you reasonable coverage, 40 meters through to 10 meters, and 6 meters as well. And it's quite a reasonable performer. 20 meters, it really excels. 40 meters with something 29 foot long, as you might imagine, it's not as good as it could be. So I wondered what you could do to an end-fed vertical antenna to try and get rid of as many losses as possible and make the antenna as efficient as possible. And while I was trawling through the internet, I came across a piece by Tim Hughes, G5TM, who's done a fantastic YouTube video on the 43-foot end-fed antenna. Now, mine's a slightly different design to his, but his work and some of his data is included in this slideshow. So, what does a 43-foot antenna look like? It looks like this. And because this is disappearing into space, the top of it is up here. So it's a big one. But if you have a small garden, then, you know, it's fairly low visual impact. If we can get it up and take it down in a day, which you can, in fact, that takes about 10 minutes to erect. It's quite a useful antenna. And I've also added to it, rather than put ground radials on it, elevated counterpoises, which I'm going to talk about a little bit in the slideshow. So this is what it is. It's the Rybakov on steroids, 43 feet long to the tip. And you might think, well, how the hell do you get a 43-foot antenna into the sky? And well, you do that with a 12-meter spider pole, and then you bolt a bit on top of it. And when that starts swinging around in the wind, you know about it. And you're going to pick a calm day if you're not going to guide this thing. So it's a bit lively. Okay, so let's get into the nitty-gritty of the show. So what do we actually want from a vertical HF antenna? We want multiband operation, 80 meter to 10 ideally, including the warp bands. We would like good efficiency and low losses, obviously. We'd like low angles of radiation with a bit of gain where possible. Well, a long antenna will give you that, because on the higher frequency bands it becomes multiple wavelength, or a wavelength and a bit, 5/8 perhaps, or 3/4 wave, and this can give you some advantages with radiation angle. Ease of installation and relative low cost, which it kind of is. Spider pole will cost you about 90 quid. You've got to hold it up with something, and if you do what I do, which is use a remote tuner, that will cost you another couple of hundred quid, but it's still not out the way. So relatively low cost. It's quick to erect and lower, which it is, provided you're brave and you hold your breath, and it's got low visual impact, because once it's up, it actually doesn't look that bad. As you can see here in the photograph, it almost disappeared against the skyline. A few neighbours were grumbling and looking over the fence and wondering what the hell I was doing. I went up and up and up and up into the sky, but it has fairly low visual impact, far less than my doublet, which is dangles all over the garden. And small footprint. Now, small footprint is important because with a vertical antenna, you typically need a large ground radial field. And this thing can extend out in all directions, ideally, maybe 17, 20, 30 feet. That's not what I call a small footprint. That's a radius, 30 or 40 wires extending out to 30 feet in all directions around your garden. You won't be friends with many people, including your wives. So what do you want to avoid? Unacceptable ground losses. And it's this that kills vertical antennas more than anything in the world. Ground loss. Loss of efficiency. Efficiency of an antenna is basically the radiation resistance divided by the radiation resistance plus losses. And nearly all those losses are ground losses. You're warming up the garden and killing the worms. There's a little bit of resistive ohmic resistance in the wire itself, but nothing at all like a typical Yorkshire back garden. And mine is one of the very worst, because I sit on top of what used to be pond quarry at Hove Edge. And all it is all the way down sandstone, plus all the crap the builder could dredge from anywhere, including brick dust, scattered on my garden with a bit of black soil on top. So we want low radiation resistance. We want to try and avoid. Radiation resistance is a function of antenna length to wavelength. And radiation resistance is the good resistance in an antenna that delivers the power into radiation. It's like an imaginary resistor, that the more current you pass through it, The higher the resistance, the more power it will dissipate. So what to avoid low radiation resistance, which is typical with very short antennas. Some of these little tiny antennas on 40 meters that are this long with a loading coil, radiation resistance of about 2 ohms compared to about 48 for a decent antenna. So you can see the problem. We want to avoid extensive ground radials and multiple conductors, unless you've got a garden or a field behind you. You can put these things out in. Because if you're putting a temporary antenna up, we don't want to put 30, 40 radials out, which is really what you need. And we want to avoid poor matching at the feed point, transformer losses. And one of the big problems with the Rybakov style of antenna, the end-fed non-resonant long wire, if you like, is the fact that you have a fixed ratio transformer, hopefully, theoretically, if you read the textbooks, transforming 450 ohms down to 50 ohms. What you've actually got is a 9-to-1 transformer trying to transform 40 ohms down to nothing, because that's what really happens. So we want to avoid these transformer losses. The transformers are not efficient, crack away across the band, and not only that, once you start to get complex impedances and phase shifts going on, these things don't perform very well. If we have a high voltage standing wave on the feeder, then we will have high dielectric losses in the feeder. So that's where your losses come from a poor transformer matched at the feed point. You get high VSWR losses and you'll lose 3-4 dB on the feed cable, which is half your power. So let's have a look at the map of where all these losses occur. Starting off, if we have a short radiator, we have a low radiation resistance. So we're going to struggle to convert some of that power into radiated energy. If we've got a poor ground, which typically we have, we'll have a high radiation angle. The reason being, you have to create in the ground a good conductive surface that acts as the mirror to create the other half of the dipole, the invisible, the virtual dipole going down to the ground. It's that gives you the low radiation angles. So we need to have good conductive ground, and generally we don't. So we lose out with high radiation angle. We end up with transformer losses because we have a fixed ratio transformer down here. That gives us a high VSWR on the cable. So we have VSWR losses going back to the transceiver. And then we've got matching losses in the ATU itself. You know, there's not perfect machines, and a lot of the losses are in the inductors inside the matching unit. And then we come onto the ground itself. We took these radials out and we tried to capacitively couple into poor soil. Now, all we're doing with this is simply trying to enhance the ground conductivity with ground radials. We're just trying to make it a wee bit better, closely coupling that wire into the ground, hoping the ground will conduct that bit better. And generally it doesn't. So we have ground losses, and this is the series resistor that lowers the efficiency of the antenna. So all these things going on that can spoil what could be a good antenna. So how do we fix that? First of all, we get rid of that transformer. That's what we need to do. We move the ATU where it should be to the bottom of the antenna. Then connect the radio where it should be to the end of the cable. This cable is now matched at 50 ohms. The matching loss moves over here. So we haven't moved that. We haven't lost that, unfortunately, but we have lost that. So we get rid of the VSWR loss on the cable. So we're already winning. Next thing we're going to do is we're going to remove the ground dependency of the coax. Get rid of the ground radials, get rid of the ground loss, and we're going to fit an elevated counterpoise, which I shall come to in a moment. When we fit the elevated counterpoise, now the antenna capacitively couples to the counterpoise. This thing is a huge capacitor plate. It couples to the ground, yes, but it doesn't try to induce high current into the ground, which is where the losses are. It acts as part of the antenna. The other half of the dipole is now a wire, which is what we want. So this performs a counterpoise against the antenna itself, and it allows the antenna to couple efficiently, capacitively into the counterpoise for the return current back to the transmitter. By doing that, we lower the radiation angle. So not have we gained a few dB by lowering VSWR losses, we've also lowered the radiation angle and gained a couple of dB there. And it starts to add up. So if you do all these things on a very big antenna, it's amazing what this thing will perform like. So I need to clarify a few definitions, because a few people get confused with this as to what these things are. First of all, we have a ground radial, either buried in the ground or laying on top of the ground. The ones on top are supposed to perform slightly better, but generally speaking, it doesn't matter how long these things are, they will not be resonant. So it can be any old length, typically 15, 30 feet or something of wire, as many as you can get out. And these things basically try and capacitively couple into the soil over a wide area and get that current in the soil increasing and get the current flow in the soil, but it's still warming the soil up. So while these things are great if you've got hundreds of the damn things and you're on reasonably conductive ground, they're not the best solution. The next thing we have is the elevated counterpoise, not a radial, a counterpoise. The elevated counterpoise sits off the ground, anywhere between a foot and up to 9 feet if you've got a long wavelength, but typically about a foot to 3 feet is where you want these things sitting off the ground. One counterpoise, 2 or 3 will work perfectly well. We're already saving on wire, and if we're going to put this out as a temporary antenna, this is an easy solution. So it's non-resonant still. The length of these wires isn't critical. There's a rough rule of thumb, about 15 or 17 feet for 40 meters, 30 odd feet if you're going on to 80 meters. So they don't have to be massive. And you keep them off the ground. The only problem is, of course, these things are tripwires. So what you can do is simply run them around your fence, on your boundary, around your house. They don't have to be stringing out into space. They can just stick them around the house. They are a very convenient way of loading up an antenna against ground. And in fact, if you live in a 3rd floor apartment, the counterpoise is what you'll use. You will use an elevated counterpoise. And then we have the elevated radial. Now, the elevated radial is no longer ground dependent. It's not trying to couple into ground. It's becoming part of the antenna. So this is typically anything above 0.1 to 0.2 of a wavelength off the ground. And these are now resonant. So these are cut like this thing here, quarter wave on 2 meters. This is an elevated radial. So ground radials, elevated counterpoise, elevated radial. You can do things with an elevated radial if you have an antenna which has a funny feed point impedance, 35 ohms if it's flat, 50 ohms if it's tilted down. You'll see a lot of them tilted down, and then 75 ohms if you want to bend it back on itself like that. So you can play with the feed point impedance a little bit. The definition of an elevated counterpoise, and this came out of, I don't know if anybody's read Sebic on antennas. He's got a big website. He's dead now, unfortunately, LC Sebic. And he had a friend of his who wrote in an article for him in QST and the ARRL. And he said, a counterpoise, which consists of one or more wires in a network insulated from the ground, will often reduce loss resistances, which might occur when the antenna is connected to poorly conductive earth. The counterpoise, in the case of a network of several wires, acts as a capacitor plate with a high capacity to earth, with the result of lower loss in the antenna system. That's what we want. For this reason, the counterpoise should be fairly close to the ground, and fairly close is a couple of feet. That's what he meant. So let's have a look at radiation resistance. Where the hell does this thing come from? There's a formula of radiation resistance, and it's the equivalence of a resistor. Let's suppose that I have a conductor and I have a resistor of 35 ohms, and I connect that across my transmitter, and all the power is dissipated as heat in this resistor. Yeah? And that's the only form of resistance in the system. All that power is dissipated. Now, that's not strictly true with an antenna, because you've got feed line losses, you've got the resistance of the wire itself, you've got ground losses and everything else coming into it. So all these resistances are in series. But basically, it's a function of how long the antenna is compared to the wavelength you're using it on. The formula is radiation resistance for a monopole, an end-fed antenna, 40 pi squared times the length of the monopole in meters divided by wavelength squared. Not too difficult. That works out at 40 pi squared, 395. So we try this on 40 meters for a typical Rybakov, 8 meters long. This is this lot here, 0.04. You get 15.8 ohms of radiation resistance. Compared to a quarter wavelength antenna of 32 ohms, you're already half down at that particular frequency. If you make the antenna longer, the numbers go up. We can increase the length to 13 meters, 43 feet for the super-Rybakov. And on 40 meters, we now have 395 times 0.105, 41.7 ohms. So already with 3 times more power we can dissipate by making the antenna a wee bit longer, purely by increasing the radiation resistance. And you will find that the feed point impedance of any antenna tracks the radiation resistance pretty closely. A resonant dipole is about 73 ohms radiation resistance, and that's the theoretical feed point impedance for a dipole antenna at resonance. So it does track it. Radiation resistance as a function of wavelength. Have a look at this now. These very short antennas, look, a couple of ohms of radiation resistance. As we go to quarter wavelength, we get to 36 ohms. Why 36? It's half a dipole. 72, 74 ohms, half a dipole. As we start to get to 3/8 wavelength, we're up to 210 ohms. And this is our wonderful half-wave end-fed antenna, resonant half-wave end-fed. 1200 ohms radiation resistance. That is why the end-fed half-wave is so bloody efficient. Because compared to any of the losses in the ground, there's very little current flowing. So the end-fed half-wave is an absolute superb performer with very, very high efficiency. As we start to go longer than that, 5/8, 175 ohms, 3/4 wavelength, 80, and then we get another peak up here as we get back towards 1 wavelength, twice this, it pumps up again. So we need to be driving up the length of the antenna to get the efficiency up. The efficiency, as you might imagine, as the radiation resistance goes up, we have 10%, we're starting to climb up here, look, 32%, 46% efficient for a quarter wave, 97% efficient for an end-fed half wave. That's why they're so good. So the Rybakov, the super-Rybakov, sits somewhere on here and it plays around in this area. So it is quite an efficient antenna. Then we come on to the Unun. Now, as I said, that the feed point impedance tends to track the radiation resistance. And of course, as the frequency changes, the radiation resistance changes, the feed point impedance changes. And generally, it's not resistive. Now, all the theory you read about these Ununs here, 9-to-1 voltage Unun, is that they simply transform 50 ohms to 450 ohms, which is the average impedance of a random wire, something that's designed to be non-resonant on as many bands as possible. Unfortunately, the way these things work is that it's a transformation of voltage. And as you start to transform voltages with turns ratio, you'll suddenly find out that that's fine as long as the load's resistive. If you stick a 450 ohm resistor to a VNA with a 9-to-1 voltage on it, you'll have a flat SWR curve, 1-to-1 almost. Perfect. Well, until you start to get higher in frequency when the core starts to lose out. But these things aren't purely resistive. What we have is complex impedance where we get phase shift. Where we get phase shift, the current and the voltage are no longer in phase. And that's when this thing stops becoming 9-to-1 and could be anything. 2-to-1, 3-to-1, just about anything. So not only have we problems with the impedance transformation ratio of a fixed Unun as the frequency changes, we also have this rather strange thing that it's not linear. So the SWR, we start down here, we're down at 80 meters, 40 meters, so we start to climb up, we get down to towards 10 meters, and this thing's 2-to-1 SWR before we even start. And we can't get any better than that, simply because this thing's not linear. So we need to get rid of this thing, which is what we've done. So we're testing the concept. How do they test it? Well, first of all, this is my homemade antenna mounting pole, which is a bit of water pipe. This is 3-inch 10-bar plastic water pipe with some flanges on it, and this thing's bolted onto a tilt plate and it clamps onto the side of the house. And all I do is drop the spider pole into it and I clamp the remote ATU. This is a MAT 40 remote ATU. Absolutely lovely little antenna tuner and relatively cheap, about 220, 230 quid, which is a lot cheaper than some of the other offerings. This is it here. You can see my wonderful contraptions. This is a 3-inch water pipe joint. So I've developed that'll clamp onto the water pipe just here onto a plate, and then this is the plate that comes with the tuner. And what you've got a insulator for the wire antenna here, and underneath you've got the SO239 for your radio and the remote control cable, which I think comes out as 10 meters and you can extend it. This is the ground connection for the counterpoise. Here we are. And these are two 17 feet counterpoise, which disappear off across the garden. Wrong poking stick. Right. So these are just simply held up across the garden, roughly 3 feet off the ground, in roughly 90 degrees. And that's all I've ever tested it with. As we come to look at the results later on, they work fine. Just 2 wires. They could have gone around the fence, around the house. You'd never even see them. No need for a massive great carpet of ground radials going out with this. This thing works because these are elevated counterpoises. You can get away with a lot less for the same efficiency. So that is where the ATU works. My shack's in here, behind this wall. And then how do we extend? Now 12 meters is not 43 feet. So even with the spider pole at its maximum extent, I'm 4 foot short. Now what I've done on my spider pole, I rarely use this element unless I'm using a very light wire. I put in it what looks like a giant needle, eye of a needle. This brass thing goes down about this far inside, arrowdited in, so that's rock solid. And I can use that to fasten things to without damaging the GRP pole. So what we do is we make one of these things, just a little collar, and the wire comes up 39 feet of wire, attaches to this eyelet here with a clip, and then attaches to this thing at the top with a wing nut. And stuck on top of that is this. And this is the end of an HF360. You can buy them at Moonraker for about 13 quid. And the beauty about these things is they are tapered. They don't come with a bobble on the end, so you will poke your eye out with them. So I made that. But that is tapered and it's got a very low wind resistance. So 13 quid for an extension, that gets me to 43 feet. Perfect. But as I say, it does wang about a bit. That's what it looks like, fully retracted, and it's just about on the eave line of my bungalow, and then it goes skywards at a great rate of knots. That's the tuner in place. Counterpoise is attached here. Your wire is anchored here with a little bit of cord, and then just hooks onto the top of the wire point on the tuner, and it works remarkably well. So let's have a look at why this thing performs better than the traditional Rybakov antenna at 29 feet. Well, these are Tim Hughes figures, and I'm very grateful for his YouTube channel. As you can see, because on 80 meters, the 29-foot vertical doesn't perform particularly well because it's only about 11% efficient. 80 meters for a short antenna, that's not actually that bad. But it compared to 40% efficiency for a standard quarter wave on 80 meters. We have a look at the longer one. We're up to 19%, which I can live with that on 80 meters. But look at what happens on 40 meters. 42% efficient is a Rybakov, 29 footer. I jumped to 74% efficiency with this thing. It's longer than quarter wave. On 30 meters, absolutely storming, and it really did as well. Really good on 30 meters. And then 20 meters, 80% efficient, 97% efficient on the traditional Rybakov. We know it excels on 20 meters, the Rybakov. It's almost what it was designed for. And look at these, all these efficiencies then start to climb. We're in winning territory all the way down here. So we gain a lot. If you want to be on 40 meters, and you can squeeze onto 80 as well a little bit, this thing will give you a significant increase in efficiency. That is my 128-foot doublet sitting above the house. So that's the antenna I compared it to, which you might think is a bit unfair. And in a way, it probably is. But let's have a look at what actually happened. And this is what's been so difficult testing this antenna, because the daytime bands are absolutely dire. You get occasions where early in the morning, when I've not got up and put this thing up yet, where 40 meters is lively, but the rest of the time it's been absolutely grim. So what happened on 40 meters? Switching between the two antennas, I'm estimating around 2 dB in the signal strength, going from the Rybakov to, the doublet to the Rybakov. So the doublet beat it by a little tiny bit. The only difference was, being a vertical antenna and so close to the house and not balanced, I got quite a bit of extra noise on 40 meters. About 6 dBs at the noise floor came up. But the band was QSB on the band was terrible, really, really heavy. On 30 meters, the Rybakov outperformed the doublet by 3 dB and no noise at all. 20 meters, look at this. The signals on 20 meters compared to this thing were up 12 dB. I couldn't believe it, but there it was. Absolutely excels on 20 meters. 3 dB up on 15 meters, unfortunately very little activity on the band, and then 12 and 10 meters were flat. There's nothing at all. So I can't really give you any data. I've waited a month to try and get data for this thing. And of course, I don't leave this thing up because it's not guide. And I guarantee if I go to bed, the bloody wind's going to get up and this thing's going to be banging on the roof. So there we are. They were obtained with just 2 elevated counterpoises, 17 feet long. Just 2. Had I put more up, I'm sure I've got better films out of it. But just 2 wires. If you're into a small garden and this thing, you can get a Rybakov or particularly a super-Rybakov up. It's not a bad antenna at all. So acknowledgements, Tim Hughes, G5TM and others, Sebic and a few others who've written about this antenna. He has a fantastic video on this antenna which goes into great detail as to why it works so well. And I really highly recommend this guy's work on antennas. And this is where a lot of the data has come from. He was an inspiration for me to try and copy this antenna and trying to get the losses down, which I think I've achieved with it. So an interesting constructional exercise. It would have been nice if I could have guided it and left it up a bit longer, maybe worked in the evenings when the bands were picking up. But unfortunately, the last couple of weeks have been absolutely hell for me. So that's not been the best thing in the world. So that's it, really. If you want a big antenna, build them big. Yeah. Any questions, gentlemen? We really appreciate you taking the time to watch this video. Don't forget to check the video description where you'll find additional information about the video you've just watched, along with links to products used and to the Hadi's website. If you enjoyed this presentation, please feel free to hit that like button. Maybe you'd also consider subscribing and clicking the notification bell so we can let you know the next time we release another video. Thanks again for watching.